Hello everybody and welcome back to Archive Insights. So in a lot of real-world problems, we have a whole bunch of data that we're looking at. It could be images or text or audio, whatever it is, but the underlying factor, the underlying process of that data could be much simpler and in a much lower dimensional space than the actual data that we're looking at. So a lot of techniques in machine learning, they try to compress the dimensionality of your data into a smaller space. One very popular technique that's used a lot in recent papers is called Variational Autoencoders. It is going to be a pretty technical episode, so I hope you're ready to dive into the mechanics of Variational Autoencoders. My name is Xander, and welcome to Archive Insights. So, before we dive into the mechanics of variational autoencoders, I first want to introduce normal autoencoders. So I'm going to assume that you're already familiar with the neural network architectures that we have, things like backpropagation and all of that. So what an autoencoder does is it takes some kind of input data, it could be an image or a vector, anything at all, with a very high dimensionality. It's going to run it through this neural network and it's going to try and compress the data into a smaller representation. It does this with two principal components. The first component is what we call the encoder. And the encoder is simply a bunch of layers, they could be fully connected layers or convolutional, that are going to take the input and they're going to compress it down to a smaller representation which has less dimensions than the input, and this is what we call the bottleneck. And then from the bottleneck, it's going to try and reconstruct the input by using, again, fully connected or convolutional layers. And then the loss function of training an autoencoder is simply looking at the reconstructed version at the end of your decoder network, and then you're going to simply compute the reconstruction loss with respect to your input. And by simply comparing pixel-to-pixel differences in the output, we can create a loss function and we can start training our network to compress images. And so obviously you have simple encoders that use fully connected layers, but you can just as well swap them out with convolutional layers if you're working with images or something like audio, for example. And if you look at what's going on here, if you train a deep convolutional network to do encoding and decoding of a whole bunch of images, you're actually creating a whole new kind of compression algorithm. And Google is actually thinking of using these types of networks for reducing the amount of bandwidth that you use on your phone. So if you download an image, then the full resolution image is first downscaled, then it's sent through you over the wireless internet connection, and then in your phone there is actually a decoder that reconstructs the full resolution image from the compressed representation. And if you apply this to something like MNIST, for example, then it's very interesting to see what these hidden representations are actually learning. So here you can see a bunch of images where on the left side you can see the input digits that are being fed through the network, and then on the right side all of those are reconstructed images, but you can see what happens if we change the size of the hidden representation. So if we use only a 2D hidden representation, that means that our bottleneck, in the middle of the network is only two variables, then we get reconstructions that look pretty okay, but they are very fuzzy. And the fuzziness is because you force the entire information of your image to go through two single variables. And then when you reconstruct, obviously you lose some of that detail. And that is why the images look so fuzzy. If you use more dimensions in your latent representation, then you can get reconstructions that are much clearer and much sharper, but you need more information in that bottleneck. And it's interesting to note that the exact same technique is applied to image segmentation as well. So you take an input image, you run it through your convolutional encoder, it goes through a bottleneck representation, and then it gets remapped to a full output image. But in this case, instead of reconstructing the original image, you're actually trying to target a segmented version of your image. And it's exactly this type of network that is used in self-driving cars to segment the different parts of the public road into specific objects that a car needs to detect. Okay, so that's the basic idea behind autoencoders, but there are a few very clever tricks that you can apply to an autoencoder to have it do some really fancy stuff. So imagine that you start with a normal MNIST digit. It's a clean image, nothing's wrong with it. But then you add a whole lot of noise to it, and you're going to run that noisy image through your encoder network. You get through the bottleneck representation, and then you try to reconstruct the image, but instead of reconstructing the noisy image, what you're going to do is try and reconstruct the original clean image. And if you train this network on a whole bunch of these noisy MNIST digits, you're going to try and force the encoder step to actually get rid of the noise. And this is what we call a denoising autoencoder. And so you can see here that by using this approach, you can actually train a denoising autoencoder that is very good at removing noise from input images. And denoising images isn't the only thing that you can do with this type of approach. So in this case, for example, you take an input and instead of adding noise to it, you simply crop a rectangular area out of the image and you throw it away. You replace it with white or black pixels, you feed that input image through the network, and you try to reconstruct the original full image. And this technique is what we call neural impeding. It's where you take a small part of the image, you throw it away, and then you ask the network to reconstruct whatever was there in the input image. And with this approach, you can do simple things like removing watermarks from images, but you could also remove a parked car, for example, if you are filming on a movie set in a natural setting. Okay, so now that we have the basic concept behind a normal autoencoder, let's introduce variational autoencoders. So the idea behind variational autoencoders is that instead of mapping any input to a fixed vector, you want to map your input onto a distribution. And so the only thing that's different in a variational autoencoder is that your normal bottleneck vector z is replaced by two separate vectors, one representing the mean of your distribution and the other one representing the standard deviation of that distribution. And so whenever you need a vector to feed through your decoder network, the only thing you have to do is take a sample from the distribution and then feed it to the decoder. And so to train a variational autoencoder, the loss function in this case actually consists of two terms. The first term represents the reconstruction loss. So this is really the same as the autoencoder step, except that here there is an expectation operator because we are sampling from a distribution. And then the second part of the loss function is what we call the KL divergence. I'm not going to go into all of the details because there is a lot of math involved there, but basically what you want to make sure is that the distribution that you're learning is not too far removed from a normally distributed Gaussian. So you're going to try and force your latent distribution to be relatively close to a mean of 0 and a standard deviation of 1. And so finally, before we can start training our variational autoencoder, we have one final trick that we have to use. Because if you look at the computation graph of our network right now, we have a problem. In the middle of that network, after the bottleneck, we have a sampling operation. There is a node there that takes a sample from a distribution and then feeds that sample through the decoder. But the problem is that you cannot run backpropagation, you cannot push gradients through a sampling node. So this is an issue. And so in order to run your gradients through the entire network and train everything end to end, we're going to use what we call the reparameterization trick. And so the trick goes as follows. If you look at the latent vector that you're sampling, you can actually look at that vector as the sum of a fixed mu, which is just the parameter that you're learning, plus some kind of a sigma, which is also a parameter that you're learning, and then multiplied with an epsilon, and this epsilon is where we're going to put the stochastic part. So this epsilon is always going to be standard Gaussian, it's always going to have 0 mean and standard deviation of 1. We're going to sample from that epsilon and then multiply it with sigma, add mu, and we have our latent vector. And so the clever thing here is that now our mu and our sigma, those are the only things that we actually want to train. So there we have to be able to compute gradients and run backpropagation. But that epsilon, well, that doesn't really matter because we don't want to change that epsilon ever again. That epsilon is a fixed stochastic node. Okay, it's still stochastic, but we don't have to run backpropagation through it, so it doesn't matter that it's a sampling operation. And so this is the reparameterization trick, where instead of having a full stochastic node that is blocking all of your gradients because you can't do backpropagation through it, you're going to split it up into a part where you can do backprop, and then another part which is still stochastic, but which you don't want to train because it's fixed. Pretty clever, right? So let's take a quick look at some code in TensorFlow. So here you can see the encoder network, which is training two sets of parameters, the means and the standard deviations of our distribution. And then in the actual autoencoder, we're going to do a sampling operation from that distribution to actually get our latent vector. And then you can see where they compute the KL divergence, and then you're actually going to compute your loss and backprop through it. Alright, and so before we go and look at some visual results of what you can do with variational autoencoders, I want to note one final thing. There is a new class of variational autoencoders which has a lot of promising results that's called disentangled variational autoencoders. And the basic idea behind this disentanglement is that you want to make sure that the different neurons in your latent distribution, that they are uncorrelated, that they all try and learn something different about the input data. And so to implement this, the only thing you have to change is add one hyperparameter through your loss function that weighs how much this KL divergence is present in the loss function. And so in the disentangled version, the autoencoder will only use a specific latent variable if it really has a benefit. And if it doesn't benefit the compression, then it will simply stick to the normal. So in order to show the result of a disentangled representation, let's look at a very simple dataset. The dataset consists of images that are generated from 4 latent factors. So you have the x position, the y position, the size of the objects, and the rotation of the object. And by just picking a sample from that distribution, you have 4 values, you can just generate an image that is generated from exactly that hidden representation. And then the idea is if you train a disentangled variational autoencoder, what you would like to see is that the autoencoder is able to reconstruct and come up with that exact mapping of those 4 latent variables to encode the information in its inputs. And it turns out that if you use the normal loss function of a variational autoencoder, it simply comes up with a whole bunch of latent spaces, but it's not really finding exactly those latent variables that we use to generate the images. But if you disentangle your representations, it gets much closer. So here on the left side, you can see that by increasing that beta factor in your autoencoder, you're actually forcing your autoencoder to map the information onto only a few of those latent variables. So instead of using all 10 of them, the autoencoder only uses 5 of the latent variables to encode the information. And you can see that the first one represents the y position, the second is the x position, then you have the scale, which is the third one, and then in fact there are 2 latent representations that the autoencoder used for representing the rotation of an object. But interestingly, all the other latent representations, even though they are still fixed at a Gaussian distribution, and this is because they weren't really necessary to encode the information of our input. And here you can see a really interesting result where they applied variational autoencoders at Google DeepMind on their DeepMind lab environment. So you can see a 3D world where an agent can sort of run around. And what they did is they compressed the input images that the agent is seeing into latent space, and then they reconstruct it. But what you can also do is you can start changing the latent variables and then see what happens to the reconstruction. And so it turns out that if you use a disentangled variational autoencoder, then changing the latent variables actually corresponds to some very interpretable things. So here you can see that changing the first latent variable actually changes the color of the floor, but nothing else. And then there are other latent variables that correspond to turning to the left or turning to the right. And there are even some that change the rotation and the identity of specific objects that the agent is looking at. And in contrast, if you don't use this disentanglement, then whenever you start changing a latent representation, everything starts blurring up in the image, and it's not really clear what this latent vector was trying to encode. And so I think this image sums everything up. On the left side, you have a disentangled variational autoencoder, and you can see that if you change the first dimension in your latent space, then the face is rotated, but nothing else changes. If you do the same thing in a normal variational autoencoder, the face also rotates, but you can see that a lot of other stuff is changing as well. And then as a comparison, on the right side, you can see the results for a generative adversarial network. And so the holy grail of disentangled variational autoencoders is to have some kind of a network that can extract very useful causal features from a very high dimensional space, and then use those features for some task that it's trying to learn. And the hope is then that those learned features will also generalize to domains outside of your training data. And so one of the common domains where people are trying to apply variational autoencoders is, for example, in reinforcement learning. Because the whole problem in reinforcement learning is that you have very sparse rewards and it takes a really long time to train anything. So by using this variational autoencoder as some sort of a feature extractor, the hope is that you can actually run your agent on the representation, on the compressed representation, instead of on the full input space. And so when using this in practice, there is actually a very clear trade-off. If you disentangle the latent space too little, then your network is sort of overfitting. Because you give it too much freedom, it can just learn how to reconstruct your input training data, but it won't generalize to unseen data in new cases. On the other hand, if you disentangle too much, then you actually lose a lot of the high definition detail in your input, and this can actually hurt performance in a lot of applications. So personally, I find this a really interesting idea, and I'm very curious if this will lead to some types of networks that can learn to extract very useful low-dimensional information from very high-dimensional spaces. Because in the end, we want to train agents that are able to understand the world by compressing a whole lot of information and then learning useful behavior on that latent space. Alright, congratulations if you made it to the end of this video. I hope you learned something. Don't forget to subscribe. And I'd love to see you again in the next episode of Archive Insights.